Hi to everyone. Good evening. First thing, I would like to thank Vistaprint. They are giving us a very good place and some snacks after if you want to have some. They are on the entrance. If you have any questions about Vistaprint, you can talk with Frank, who's here. Okay.
So I'm Frank Tobias. I'm a software development manager here at Vistaprint. And Vistaprint, if you don't know about us, we just make a lot of printed products. We build a lot of software to connect people to each other on the internet so that they can print things for their small business. We're based here. We're hiring. If you have any questions, let me know. Thanks.
Okay. Well, today we have Christopher. I have to say we have him for sure because he's living in Barcelona for a while. Maybe not. Well, yeah, just for a while. Maybe he's coming back. He doesn't really know yet, I think. He's going to introduce us to TensorFlow, which is a great library. And he's been doing research in astrophysics for a while and with machine learning. And, well, I don't know if you want to say something.
I can introduce myself. Thank you, Alex. So I'm Christopher Bonnet. I work at the Institute for Higher Energy Physics at the UAB in Barcelona. And I'm a physicist, so I probably know less statistician than a statistician, stats than a statistician, and I know less programming than a programmer, but I know more of those than the universe, probably the typical data science profile. So today, the idea was to just give this is a gentle introduction to TensorFlow. So if you actually work in deep learning or have used the library a lot, you are unlikely to learn anything new. I use it. I try and use it at work, but I do astronomy, so I can only use it where I need it. I don't do research in deep learning, but I do enjoy working with it compared to older deep learning models like writing YAML files in PyLearn2 or something like that. I think let's get going.
If you have any questions, please. Well,
yeah, feel free to interrupt. Right, it's supposed to be a bit interactive, and also given that the fact the notebooks is, meaning you also can try stuff yourself during the session. It's gonna be partially slides, but also partially notebooks, so I think a few months ago, I got in touch with Alex and said, hey, we should do an introduction to TensorFlow. And then we discussed it. And I think just afterwards, there were... all right, okay. All the tweets mentioning our name are going to show up here. There was a Stanford lecture also, actually, Introduction to TensorFlow. So if you have seen that lecture, this is loosely based on that lecture. So... you actually know that. I've also given the link in the notebook, so you can actually look at that. That will go slightly further than we will go. So what's TensorFlow? So the essence of it is a deep learning library, open source by Google. So if you want deep learning and you want to use Python or C++, then TensorFlow is one of your options. Sort of on a more basic level, it's a mathematics library that works with tensors. We can go into what a definition of tensor is, but we're just going to assume right now, practical reasons, a tensor is something that can be represented by a multidimensional array. That's sort of kind of nice and rather simple to understand. Sort of one of the nice things about TensorFlow is that it sort of can calculate derivatives. So if you want some cost function you want to optimize with derivatives, then TensorFlow will do that for you with different types of optimizers. So that makes it actually nice and easy. To some respects, it's very similar to NumPy. So if you are familiar with the Python, the PyData ecosystem, it shouldn't be too hard to understand the syntax of TensorFlow. So that makes it an easy transition. Although one of the large differences we'll see is that in TensorFlow you need to explicitly evaluate your expressions, and in NumPy that is inherent to NumPy. So there's sort of the 2-minute introduction. So what you do in TensorFlow is you define actions on tensors. And once you define the action on tensors, it puts that into a computational graph. And to know the entire output from your graph, you have to explicitly run it in a context. So by doing TF.'s interactive session, you actually you open a session that's your context, and you could have several sessions open at the same time, but I've never done that, and I don't think many people do that. And then, so it's similar to NumPy. You can here define a 2x2 array with ones, and if you actually just print A, it's just going to tell you that it is, it's this kind of object. It's got this shape and it's got this data type. It actually doesn't print you out, an array of 1, 1, 1s. That's because it hasn't been evaluated in the graph. You're not asking the graph to execute the calculation and give you back the results. How you do that? If you have an interactive shape, you can do evaluate, and that will actually give you the content of the vector A, or tensor. So if you're working a notebook, it's easiest to use the TF.interactive session, because that allows you to use evaluate. When you actually write a large program, then we'll see that later, we'll actually use a different kind of syntax, but it's the same. So here, for example, is a different syntax. Would say, with TF session as session, you would do, and this is what if you would run deep learning models, this is what you would run. You do session.run, and then here the graph or the action which has the graph defined. That's what you would execute. But here you can see they actually give you the same. They give you the same output. So eval is the same as session.run. Open close brackets A. I think. So I think this is also in the notebook, so you can execute these yourself if you want. I'm going to try that now. I suggest you do the same. You can, yeah. And if you try and do eval without the session, we can try that actually. Oh, that actually works because I've probably got interactive session open here. Yeah. Okay. But if you wouldn't have that, then it would actually fail. It would tell you that you don't have a session open and it can't evaluate what's in there. So this parameter that we just used here, this A is basically a constant. Similar to a constant, and in here, for example, here's what happens when you no, that's not the same. But in TensorFlow, you have variables. Basically, they are variables similar to what you have in a programming language, and you have to initiate your variable, and then you have to define it, initiate it, and then afterwards, once it's in a graph, you can evaluate it. Now, a variable is we can define the variable. This is actually the same. Well, 0 is array, and we can give it a name, just like in a programming language. This is the TensorFlow name. This is sort of the name in your Python, and they are not linked together. So they live in a different scope. This lives in your Python scope, and this lives in your TensorFlow scope. So when you work with variables, and variables are actually you can alter your variables. A constant, like in an NumPy array of ones and zeros, stays an array with a vector or a tensor with ones and zeros. A TF variable is actually, you can actually change that. So, but you need to initialize them. So you have this session here, and then you can define your variable. And here, within the session, you initialize all your variables. If you don't initialize your variables, you don't have access to them. And then here you can evaluate them. You can evaluate it. Now here we just put TF zeros, with 2x2 matrix here. So that's the difference between constants and variables. And when you're going to do any kind of deep learning, basically you'll be using variables. So that's the difference between constant values and variables. I think that also should be in the notebook. I think in the text I had the variables within the session. It doesn't have to be within the session. You can just define it outside the session. There's no need for that to be defined in the session. So, as you can see, that runs as expected. And there's a second example. Actually, you can see here is like an example how to use it as a counter. How you would you could write the counter in TensorFlow. So you define your variable, it has a name, define a new function that takes state and adds, it has the tf add, you have a constant, and then you assign the new value to the state. So assign allows you to update the value. So it doesn't actually, it's not that you say state is state plus 1, you have to assign it. So new value is now assigned to state, and actually update will actually give you the new value. If this returns the new value, and then you can actually you can run this and you can see how it updates, and then you get a loop going from 0 to 3.
You can mix constants and variables. You're mixing them, right?
Yeah. So you're adding a constant to a variable. Yeah, but you couldn't add a variable to a constant, I don't think. Because if it's defined as the variable is defined as a variable, so that's the difference here.
Okay. And if you use the plus, it doesn't understand that you are adding something, right? You have to use
in some cases I've seen it work. In other cases I've seen it not work. So I'm not really sure where how the overload works and when it doesn't understand it. So if you want to be sure to work, you would always say tf.add or df.sub. But actually, in the example later on, we see we do a minus something without doing tf dot, and it actually interprets it fine. So, so yeah, this is the example that we just run. Now, another question is, how do you get your values into your graph? And there's several ways of doing this here. We're actually adding, here we're doing an additional multiplication, and then the inputs here are constants. That's obviously not something you would ever use while actually writing your model. So there's different ways of actually putting it into the graph. You can convert NumPy arrays to tensors with tf-convert to tensor. So that's quite easy. That's something you actually might use in a toy model or something like that you're working with while you're developing. Although the somewhat default way of putting data into your compute graph is using a feed dictionary. This is, by the way, this is the compute graph from the previous example where you have 3 inputs, and then here these are summed, and then the graph calculates the multiplication. I don't know if you noticed that in the previous example here. No, not this one. In session.run here, you can put multiple, basically multiple parts of the graph in there that you want the output for. There's no reason that has to be just one, because it actually returns you the multiplication and which is the addition. So you can add anything that you have defined parts of your graph. You can get out of that there. So.
The order is important in the session run?
Yeah, so that's going to be multiplication, and that's going to be your, yeah, so.
But if you put in the other way?
I think that's okay, that's all right. Yeah, it's not that because, no, I think that's okay. We can try it actually. But that's a list anyway, and the list doesn't have a order in Python, so yeah, that's fine. As you can see, just switch the arrays around. So
it calculates these variables through the dependency graph, but so if you start at the one at the bottom, it evaluates the entire graph. If you then take one that's also in the same graph, does it re-evaluate that subgraph?
No, I don't know actually. I don't know. I don't know enough of the internals of TensorFlow. I would. My guess would be yes. That would be my guess, but maybe someone else who knows more about internals can help you with that. Because I don't think it would store all the intermediate results. That would be my guess, but I might be wrong. So yeah, so this is the constant one that we saw before, and we just run. Here's actually we convert from NumPy to a tensor, And actually this one here is sort of the default, is with the feed dict. So what you do is you have to define a placeholder. You say, well, actually I'm going to have a variable that is going to be of this type, but I'm not going to tell you what it is. I just need, it needs a place in the graph. I can sort of add a node to the graph. There's a multiplication of those two inputs, and then within the session, I'm going to actually feed the values to that graph. So that's the feed dict. So that's the standard way of feeding your values into the computation graph in TensorFlow. Also allowing you for more flexibility, as you can see. Afterwards you can fill in whatever you want there, right? So. And here it's that one was just a single value, now it's two values, and obviously you can do any kind of shape you want. So that's the default way of getting data into a graph. Any questions till now? Is that all working for everybody who's got a laptop? Yeah, all right. Yeah, and this is a graphic representation of the graph that we did before. These are the placeholders, and this is just the feed dict here, the feed dictionary, which is then sent to the placeholders, and then actually computes the node in the graph, and then is the output. Another thing that TensorFlow uses, you can define variable names and scopes. Now, I haven't used this very much myself, but apparently when you make very complex models, you want to use scope and names of variables. So I learned it myself, and I'll cover it. You might want to read up more about this. So you can define a scope, and within your scope, you can define variables. These variables are only accessible within that scope. Within a scope, variables names are unique, and I mean the variable here, we get variable. Get variable here is actually the same as make variable, and we'll come back to that later. You can also say get variable and say reuse, meaning you can share variables, you can recall that same variable. But for now, just read this as make variable v, and you can here there's a scope within a scope, and actually that means that the name of the variable now becomes foobar v. The zero behind it I don't really understand. But the point is that within one scope, you can only have one, your variable names are unique, period. In the second path here, we have reuse variable. This means that, so when you call get variable, it means make variable, unless your scope says, I would like to reuse the variables, then you actually look if that variable exists. If it exists, you go and get it out of the graph. It's like a lookup, but only if the scope has reuse variables. If not, it's gonna complain that it already exists. I think that's the last cell. So here, for example, you make a scope. You say get variable, and this name can be different, but this name's the same, and it's going to complain. It says this variable exists. So within the scope, each variables are unique, and you can access a scope, with a scope like this. I would like to get my variable, and then you can get back out of your scope. And apparently this is needed for when you make very complex models. Any questions about that? Is that clear? Yeah, that's it for the first notebook. Also don't have any slides anymore. So, what I did is I coded up linear regression, which is very easy to do in TensorFlow. But besides that, I've actually, before we actually get to the part of linear regression, I've made an example of all the functions used to do linear regression, so you can play around with those and see how they work. So that gives you kind of a bit of a better idea what actually happens when we code up the linear regression. So we can execute. Well, this is just some imports. Here I've used a slightly different syntax. So previously I used with session as session, which is nice because it actually closes the session. Here I explicitly open it and I explicitly close it. So the with sessions, like with file open, you can do stuff with a file, and at the end in Python will automatically close the file. You can do the same with sessions. Here I explicitly, I open the session, I explicitly close the session. Yeah, these are just these are some of the functions we used to do linear regression. They are sort of very similar to NumPy functions. So addition, multiplication, take the square. Reduce mean means we take the mean along some axis. And usually you would reduce the dimension by 1, but you can also keep the dimensions, meaning you keep the original dimension of the original vector space. Here we do it. We're gonna which is the normal one. We keep dimension false. Here we do the mean, but we're also you can choose the axis of which you take the mean. Then we've got we keep the dimension true with we take the mean over the first axis, and here we keep the dimensions and we take the mean over the first axis, and that is the 0th axis. So these are the ones I defined, and then here we can execute them, so actually you can see what output that gives. Now our when we're taking the mean, we just got a 2x2 matrix full of ones. So the mean is 1, but if we keep the dimension, this is the normal one, right? Where we just take the mean. But if we keep the dimensions, you can see that it's like a nested, basically a sort of a row within a column. So it gives you some idea what it does with dimensionality. TensorFlow is kind of finicky about its dimensions. It wants them to match exactly. NumPy will do it a little bit easier. NumPy, 2 of your dimensions match. It usually does the correct thing. TensorFlow is a bit more annoying with that. So you got to often sort of dimension things pop up where you think like, hey, this works in NumPy, but TensorFlow is a bit more annoying about that. Okay, so actually these are more than all the functions you need, with some more examples that you need to do linear regression in TensorFlow. So we'll make some random data. Maybe that's a lot data. You don't need to have that many points. I don't know how fast the cloud stuff is working, but it shouldn't be. So basically we're going to fit a straight line to this, machine learning statistics 101. So we're going to find, here we define our placeholders, x and y, and the default is float 32. Depending on, I think some GPUs can use float 16, but the default is float 32. And then we're going to define the variables. This is the slope we want to find, this is the bias. We're going to initiate it with a random normal, and we're going to give it a weight, a name. One is the weight, and the other one is the bias. And then this is actually, the prediction out of the model would be the multiplication of the x values with the weight, and then added with the bias gives our linear model. So simple as that. What's our cost? Our cost function is squared loss. So this is the y prediction from our model, this is the y from our data, and then we square it. Here is like we're not doing tf.sub. So here's an example where it interprets that perfectly fine. And then obviously we're taking the mean of that. So that's the cost function. And then here, that basically gives all the stuff. That's defined our mathematical model of the linear regression. Then we sort of got to do some machine learning on top of that. We've got to choose an optimizer. You can do, there's many optimizers in TensorFlow. This is a gradient descent. So you say, I want gradient descent with a learning rate. You can now I like to minimize the cost, and your cost of function is defined here. Or you can use the Adam optimizer, which needs less tuning, which tends to be the default. So you can just switch those out very easily. So that's your optimizer. Then you have to initialize all all the variables. So those are for the ones that we had those placeholders. And then you can, well, here you actually run this in it. And then you actually do your loop. So for each loop, the graph is executed once. The optimizer returns the gradient of the cost function with respect to the weight, and then adjust the weights according to whatever optimizer you use. So your weight becomes plus or minus some delta, the gradient. So optimizer 2, actually that's optimizer 2, I don't know why it's commented out. So you use the Atom optimizer. This is your feed dictionary. So this is these are you wrote the placeholders, and this is the NumPy data. And then you can just run that 10 times, and then you can see what the outcomes is. This is the true threat, this is the true slope, and this is the true bias. I'll execute this again. I don't know if I executed this. Well, probably was still in memory, all the other stuff. All right. What's not working? Must be the value placeholder tensor placeholder 2 type float. All right. I'm just going to restart my kernel. Optimizer 2 is not defined, so that's not that weird. So it's going to crash again. Is that working for you? Yeah, it's getting the right bias and slope values. There you go. Thank you. Bye bye.
Can you specify which variables do you want to optimize? I mean, you could have like a fixed intercept and.
I think if you make them a constant, I think they stay fixed. You can't update them. I've never tried that. So if it's not a variable but you define them as a constant, then they can't be changed. I think so. That would, but I haven't tried that.
You have to put like an intermediate step, like taking the value through a constant, and then there are some algorithms that first do a gradient descent on one set of variables, and after another set of variables, and after the first type of variables, and so on. They go switching. So you have to make some intermediate steps, or you can say calculate the optimization with respect to these variables. You could fix them.
I'm not sure. I'm pretty sure you could fix them. Not quite there yet, are we? Let's do different.
Could you reduce the number of your data names?
Yeah, maybe. But I run the whole notebook again, so it should be.
When you have less data, it's harder for it to find the correct value. But now it just found it.
Yeah, I changed the optimizer, so maybe stochastic gradient descent is better than Atom when there's not much data. I don't know. All right. So that's linear regression in TensorFlow. So that's pretty easy. When I first went through this exercise, I thought it was gave me some idea on how stuff works in TensorFlow. So.
TensorFlow has something like setting now, where you can fix the random numbers that you are generating in order to replicate again the.
Yes, yeah, you can set the seed, the random seed in TensorFlow, and I think you can do it a global seed, and then even within each scope, I think you can also set the seed. So I think in this notebook at the end, there's something about that. So you can, for example, for some action, and I think you can also set sort of a global random seed. So yeah. Any other questions or remarks? Okay, and this is the last example. This is k-means clustering in TensorFlow. And I've basically done the same thing. So I've gone through, I make small examples of all the functions that TensorFlow uses to code up k-means, and afterwards we put it all together, and then we'll actually execute it and then see how well we do. So some of these are slightly less intuitive than in linear regression. And the first time I looked at these, is like, what does this do? I have no idea. For me, it was useful to actually take these functions out of the whole exercise and look at them individually. And although they're quite well explained, actually I think they're generally very well explained in the documentation. It's kind of nice to be able to play with them in the notebook. First one that's actually interesting, shuffle vector. Now it's not that hard, you just shuffle your vector randomly along the first dimension, although we'll have only one dimension here. So now slice vector will take a slice where you're first from a vector where this is your starting position and this is the length. This is within one dimension, so that's that's quite easy to understand. But if you go to multidimensional, means you'll take from the first dimension, start in 0. The second dimension, it will start at the first position, so you're going down one row in 1 if it's 2-dimensional, and then length 2. So that's, in this case, it's a 2x2 vector, so it will take both rows, and it will take from the starting position 2 more rows. That slice and then expand dimension actually adds an extra dimension to your vector. That can be useful if you need to do calculations and they don't have the same dimensionality. You might need to add 1 dimension to your vector. So these are the results. So this is the 1D vector we're working with. This is the 2D vector we're working with, and I think slice. So what we do is I think we had 0, 1, meaning that we started in the first dimension. We start from 0, means we start from this row. Then we did 1, meaning we start from 1 in, and then the length of 2. So this is the tensor that's returned. So that's the slice 2D vector. And then the 1D vector was kind of easy because I think we started by 1 and then 2, 3. Oh no, this is the shuffle one. So yeah, we just took the first 2 elements from that. And then here we've added an extra dimension to that first vector. So. Here are some more, though some are the same as previously. Subtraction square, reduce sum, and then this is argmin. So it takes returns the argument of the minimum value along this axis. So this is the 0th axis. So we'll return, and in k-means, that's basically you want to know the minimum distance to your closest cluster, right? That's when you know. So that's where that comes in. And then we can run this again with TS session. So this returns in this array, if you want the minimum argument of the minimum value, which is 5 here, so it should return us 1, and it actually returns 1. So hey, they know what we're doing. They know what they're doing at Google. So that's good news. Let me try and execute that. That works. Here are some more. Equal returns a Boolean array where it is 2 arrays. Will tell you if the elements it does an element-to-element comparison. So this should be a Boolean array where everything is true. TF where will give you the location of the true values in a Boolean array. So it will actually first have to say where are my true values, and then after that you'll actually have to get the indexes of those array basically. Reshape is the same thing as in NumPy. You can just recast your vector in a different shape. Gather is basically it will take here from vector A, it will return a new vector, and the first element will be the 3rd element of A and the 0th element of A. So it takes a sub part of a vector. and then concatenates two arrays, and then you can define which axis you want to do it on. Yeah, we create variables. Yeah, assign. We've seen that already before. We saw it in the first example. Actually, assign assigns the second value to the second variable to the first variable. And actually, the value here returned by assign is the second value, the one that is assigned. So that's used internally also to update the weights when you do when they actually do optimization. So here we just compared vector A with A, so they're all true. Where is it true in all locations? This is reshape. This was gather. So this, I think, do I have the? No. Yeah. So I said gather is just you tell which elements you want from the array, and it will return you that array with just those elements. And then the concat in the different dimensions. So.
What does this reshape mean?
Reshape, just imagine you've got a one-dimensional array with 6 elements in it. You can reshape it to an array with 2 by 3, a 2-dimensional array with 2 rows and 3 columns, or the other way around.
Okay, but they weren't the same values as in the vector A.
They should be. Maybe, did I reshape? I've got several. Did I reshape?
We changed.
Shape A, yes. This is, I think it's the top one here, because this is A. So 21.5, 12.33. 21.5, 12.33, yeah, so just change the shape, yeah. Okay, here we just make some data for the K-means clustering from some random multivariate Gaussians. Put the data together, we plot it and put it all in a data frame, panel data frame, so for easier bookkeeping. That's that. We can change this now if we want. Do we want to look for 2 clusters, or do we want to actually look for more clusters than there are? Do we want to get it right, or do we want to get it wrong? Any preferences? Right? Right? Okay. So we transfer. So here, what we're doing is we're putting the. So cluster is, I think, all the data here, right? Yeah. So cluster is all the XY data. We're putting that in a constant. That's not the data that's going to change, so that can be in a constant. And then here, we're shuffling the vector. Then we're taking the slice from in both dimensions. We start at 0, and then we're taking basically the first n elements of that. So it's basically randomly assigning the centroid to one of these elements as a starting point in the K-means clustering algorithm. And then this is another useful one to get, is a get shape. Get shape you can always call even without a session, and it also might know, if it doesn't know what the dimension will be, we'll put a question mark there, so that you know that it hasn't inferred yet the actual correct size. Yeah, we're gonna get it right? So we've got two centroids. This is what I talked about, the trickiness of sort of TensorFlow with dimensions, because the normal dimensions, I think 2002 and 22, and TensorFlow won't allow you to subtract or sum those together, so you have to add in an extra dimension to do that. It's not very pretty. So you expand the dimension of the vectors and the centroids, and then you've got these, 3-dimensional arrays, and then this is basically, then this line here calculates all the distances of your vectors, of your xy, with respect to the centroids. So this is it does the so that minus that, and then it's this minus that squared, then reduce sums. So we sum up all the distances, and then we assign each object based on the minimum distance to. So we'll use the minimum distance to assign later to which cluster it belongs. And we can see that distances is indeed 2 times 2000 here, which is correct. This is our XY for 2000 objects. The assignment is just the argmin. Then here comes a horrible one-liner. This is one line to get all the mean values. This is the one to get the new means of each cluster, which will be your new center. And I've written it out here line by line. So first, this is internally what you do. So where the assignments are equal to 0, that's now your Boolean array. So we put it before. From the Boolean array, we're actually going to find the location where they're true. That's your location array. And we're going to reshape that. We're going to reshape the location array so it has the correct shape. Then we're going to gather. So we take from the vectors, and then the reshaped location array, that returns us just the vector array where the location is 1, meaning all the objects that belong to one cluster, and then we actually calculate the mean of those values, and that's our new k-mean centroid. And here that's done in one line within for C in range of n centroids. So it does that for each of the centroids that we're trying to look for. So yeah, this is unreadable in my opinion. But if you break, this is what you do for a single one, and then that becomes a bit more manageable. And then here, for example, the shape has a question mark in it because it doesn't know exactly what dimension it will have.
Why does he know the dimension?
For example, location array. So location array depends on the dimension of the Boolean array. It's not completely clear to me why you shouldn't know that, to be honest.
You don't know the number of indexes that match.
That's true. Yeah, you don't know. Yeah. So here, yeah. Well, no, that's true. Yeah, you don't know exactly how many. Yeah, so you wouldn't know that. Yeah. Yeah, it's not the true and false. It's just the single one, right? Which doesn't have that you don't know. Yeah, an assignment is the location of the minimum distance. So here, yeah, so that's where they actually are assigned. So it takes some time, takes some operations to actually know from where it is to actually get the mean of the new cluster. So, and here we actually update the centroids. So we assign the centroids which had defined previously as these random points now to the means that we just calculated of these new clusters. So here we are changing the centroids to the means. This is then again initializing all variables, which we actually run within this session here. And we can run this for 100 steps, and then we're doing session run, update centroids, and assignment. And that will return to us. Update centroids does actually return anything of value, so we're just going to use underscore. And then the centroid variables give us our centroid values, and the assignment values will tell us to which cluster an object, a point actually belongs. So we can try and run that. And I think we got it right, pretty much. So, UP, we run k-means clustering. We can do that on a super fast GPU if you want, and
update centroids returns you everything. Well, just
this assigns the new means which you calculated to the centroids. So this just, yeah, so this says centroids are now the value that is in means.
how in each iteration of the loop the updated values are passed to the next iteration?
I suspect because it's a,
Or because it takes the values it had
yeah,
already. Okay.
it's,
So it's the same variable, it's just taking
Yeah,
the
yeah.
values of the previous.
because we initialize it as well, I think. Well, we initialize it with random. In the previous example, we initialized the weights and the bias as a random variable, and then they were updated by the optimizer.
Yeah. In fact, my question about the other order is about in this place, because update centroids depends on the assignments and on centroids. I mean, each quantity depends on the other. So it's kind of strange. Here it seems like in some sense it depends on the order, or if you run update centroids, it, as John said, gives you the whole computation. So when you ask him for centroids, does he calculate it again, or just?
So I think if you do it, so
You know what I mean?
I think within this session, within this one run, I think it doesn't recalculate it again, because these things are defined. These are basically nodes in the graph,
Yeah.
and then it will return you what the value of the node is. Now, once that thing's finished running and I run some, I can't go back and ask you what was that from the previous run, because that's been overwritten. But I think within the graph, it's going to calculate everything. It's going to probably, I think it will remember what is in each node within one of these session.run. It makes sense, right?
It's
Because it will know, each node will have a value assigned to it, and I think he has access to all of those, all the value in all the nodes.
if you run update centroids, it have to run the whole graph for obtaining the results.
Yes.
So at some point it calculates centroids, right?
Yep.
Since you are using that for the next step in the iteration, the value of centroids is stored. So you should be able to get the value of centroid without asking it to run the three variables. Do you know what I mean?
I think this is just, well, you have to ask for it, right? To get it out, you have to ask for it. It probably does run because it needs it for that
Yeah.
one. Yeah, of course it runs. I suppose you could also ask, if you have any dummy calculations in there, for example, and I think you can ask for them, right? You just say, what's x plus y, or from the first coordinate, it just always will calculate it, and I think you can ask for it. Yeah, I don't know how smart. I imagine this is properly implemented. That it runs the graph, and then after it probably sees what's the furthest down the graph, calculate that, and then get the other ones, because it will have all the dependencies, right? It will know. So it would be stupid. I'm sure it's implemented properly. I haven't looked in the source code at all, but yeah. All right. Any questions? That's all I had prepared. But if we want to try and cut up a neural net, then we can have that. We can have a go at it. Probably with copy pasting from the TensorFlow website. But that sound, yeah. So we have a go. Okay. Does anybody here use TensorFlow for deep learning in the room? Nobody? Any other? I see one head nodding. Any other libraries being used here? Cafe? Yeah. All right. Are you considering switching? Not that I'm advocating one or the other, right? And just
I've used Nano before, and then I might switch. I had used Nano before, so it depends on what you need to do. If you need to go a bit lower level, you need to do like Cafe.
to be honest, most of my neural network stuff, if I play around, I use Keras, which can either use Theano or TensorFlow as a backend, so you can switch between those two. Because depending on what you want to do, you might not need the low level that it provides, and I think that's you're giving yourself more work than it's fun to learn, but depending on your productivity, you might be better off doing stuff in Keras or any other high level instead of just the low level TensorFlow. But then knowing what's behind it can be useful.
I needed to do a hashing algorithm, so I didn't know how I could do it inside. I mean, I would have to do it in Python and then port it. I mean, in C++ and then port it to Python, and that would be more pain than just doing it in C++. It was hashing.
Right. Something that you want to be fast anyway, right? So
Yes.
in general.
Yes.
Okay. Well, it might be easier to do this in Keras, to be honest. Any preferences?
No.
No, what do you want to do now? To implement
Yeah, neural network, a simple neural network.
okay. Do you feel
No, but I'll,
okay?
that's fine, right? I don't care. I don't mind. Well, copy paste and see if we understand it and
Keras is nice. I think it would be better if you show us Keras as well, because it's useful.
I think
I want to see.
Okay, well that's one opinion, and unless people have a strong opinion the other way, then all right, okay, let's do some Keras. I should have it. All right, then Keras has some good documentation as well, I think. So Keras will not work in the online binder thing because it's not in the packages. So if you want it there, I can put it there. Let me know. It shouldn't be too hard. 30 seconds to Keras. That sounds pretty good.
If you have any questions, don't be shy and ask.
We have done the loops in Python, normal Python, and not modeled the loops or functions in TensorFlow.
You mean the optimization loops? I think that's so underneath it's all C++, and I suppose the loop overhead compared to the underlying calculation is completely negligible. So yeah, so it does have the Python loop, but whatever's in the loop is all C++. So I think that overhead is negligible compared to how large, especially if you're doing deep learning. That would be my guess. So Keras has a very easy way to add. So basically, sequential is so here we're using the Theano backend, as you can see. I think sequential is for feed-forward networks, and I think it has a different one if you want to use recurrent neural networks. And as you can see, it's very easy to add layers to a neural network. So this basically says that it was input image in 100, output image in 64. This is a real activation function, and then it goes from 64 to 10, which is then a softmax, which will give you basically will give you probabilities that these values belong in one of 10 categories. To get some, we'll have to make some fake data before I can actually fit on this. So we can use scikit-learn to make fake classification data.
While he's doing things, we are going to raffle 2 books. There was a list of people that registered for that, and I need a random number. So you tell me a random number between. Well, not really random. I mean, we're going to make a random result. So I need a seed for.
73.
73, and you? 25. Okay, 73.
Output dimension is 10.
Yes.
So the number of predictions need to be 10? Or maybe I'm doing, no, sorry, category of, like,
the uniform given features, make classification. And classes should be 10 here. Samples. It's not crashing. Shouldn't take long. Just so what we've done here is, people are familiar with scikit-learn. It's a machine learning library in Python, which also allows you to make fake data sets with correlations in them. So what we've done here is we've asked for a data set with 100 features. That's because our input dimension here is 100. Were they all important so they're not redundant? Actually, I don't know how these actually work uniformly and redundant. 10 classes and currently just 100 samples. And we've split it up in a training and a test set. Actually, that seemed to have worked.
When you say add, it adds just one before the other? I mean,
Yeah, so you add, so this is the input layer. And the input layer here expects the dimension of 100. And that's why here, so 100 features basically, right? That's why here in features is 100. So it's a 100 layer input. Then the first hidden layer of the network has 64 dimensions. And the activation function is the rectified linear unit, which is basically the zero or the maximum between 0 and x. It's basically a flat line, and at x it goes, it's just linear. So that's your activation function. And then actually straight away the output layer with the softmax activation, which basically will categorize, will give you the probability that it belongs to a certain class. And the loss function is the entropy, the optimizer, stochastic gradient descent, and you need a metric for it, which is the accuracy, which I think you can get back automatically if you want.
but this is a neuron, and after another neuron, right? And after
It's layer after layer.
Okay.
You add a layer. Input layer, hidden layer, output layer here.
And how? Okay. So you're saying just one neuron for each layer.
Not one neuron. These are the inputs. You could say it's 100 neurons.
Yeah.
Hidden layer is 64 neurons, and the output layer is 10 neurons. It's got 3 layers. And just by add, you can add your new, and you can also, if you want to add for a dropout regularization, you just do add, and then it will. It's very easy to build your neural network like that.
it's running on GPU or CPU?
This is running on CPU. So it's pretty. If you have a GPU, it's pretty easy to get it running on GPU. That's very easy with either a Theano or TensorFlow. TensorFlow has to have compute capability of 3.0. So it has to be you have to have a rather modern GPU card to run TensorFlow and GPU. Old cards just don't run. So that's good if you've got some old cards lying around. Basically, Theano, the choice is made for you. No, the choice is not TensorFlow because it has to be a new card. But it's very easy to get that running on GPU. But this is just my laptop. This is CPU, so. So it run, that's great, and the loss went down, so that's good news. What did I do wrong here? I got to do prediction X, of course. So this is just comparing the first example. If we think we got that right, I think the answer is no, because the value with the highest probability here, I think, is this one, right?
No, it's a 7.
And it's supposed to be, yeah. So we didn't get that one right. Bad neural net. I mean, well, we only run it for 5 epochs, and we had 100 examples, so maybe.
Yeah, and the number of features is really high.
Yeah, 100 features.
For 100 examples, you're not.
No, exactly. That's not gonna work. That's never gonna work. We can, well, we can make lots of them redundant. Well, then that's just noise, so that doesn't really help either. Well.
Eso es la pantalla. Mientras tanto,
We have to install. Do you wanna? Yeah.
how much time?
Doesn't take much time now.
But it's just
Yeah.
strong.
I think. Yeah.
It's not detected as a USB drive, which means you can install that.
Sure.
So when would you use Keras instead of TensorFlow?
Any rather standard and even not so standard neural network, there's probably a Keras model. You can probably write it in Keras. What Keras does is the bookkeeping for you, for example. When you say I want, for example, we did here 100 layer and then 64 layer. That's just one line here. In TensorFlow, you have to do a calculation. I've got 100 inputs, 64, and then it's mainly annoying when you do the convolutional one, right? You do the convolutional layers, you've got nothing impossible to calculate, but it's just annoying. Keras takes of that book holding for you. I'm sure there's even quite complex models. People publish Keras code for that, like ResNet, which is like the state of the art, I think, on ImageNet. Yeah, I think there's a Keras model for that. So unless you, I would say, try it in Keras and then see like if it doesn't have the functionality you need, then you'll have to go lower layer.
You cannot go deeper inside Keras.
You can call the backend, which is either Theano or TensorFlow within Keras. Yeah, you can do that. I've never done that. Yeah. So.
How would you add more layers?
You just model.add and then define your layer in Keras, and then you say the amount of neurons, the activation function, how much input and output. And actually, no, you don't have to put the input and output because it knows between where it's been put. So it actually knows the dimensionality. If it's a normal hidden layer, it will actually know what the dimensionality of the layer should be. And the Keras documentation is very complete, and it has a very active community. So there's loads of places you can, if you don't know the answers, either you can look for it or you can ask for it, and people will tend to know what to do. And it said also you can use TensorFlow or Theano as a backend, and your model stays the same. So that has an advantage.
Is it possible to export like the TensorFlow code from my Keras?
That I don't know. I do know that you can export your TensorFlow model. I imagine it can because it's just a bunch of weights which are so I'm sure you can. I wouldn't know how to do it, but I don't think it can. You can access the backend. I think it's like import backend as K, and you can have a configuration file where you define your backend, and I imagine from that backend you have access to TensorFlow, and there you can access, I imagine, everything that you need to access. So I think, yeah.
Okay, let's run the raffle. I was bored at home and I didn't know what to do, and so. This is a kind of random walk, so totally stochastic. Okay. The first one is Javier Castillo. I don't know if he's here. Javier Castillo. It's not here. The second one, oh, we are not going to see it. This is the useful part. Okay, Javier Castillo, if he's here, no? Ismael, okay, you're the first one. We are raffling these books. It's the English version of previous one, which was Hello with TensorFlow by Jordi Torres. We made, well, he's at the UPC, he's a professor, and we made a whole event about that. So, well, hope you enjoy it. And the second one, and the third one, Bernat? Ah, okay.
Yeah, I'm done.
Okay.
Unless people have more questions or comments or
Any?
One question about this TensorBoard.
Can you show us TensorBoard?
No. I've never used TensorBoard. I think it's easiest to run if you're actually running stuff on your local computer, and to run TensorBoard is very easy, which I've never done, because if I do actually use TensorFlow, I tend to use it on a server somewhere, and then you can set up a VPN to pipe it through, but I never bothered to do that yet. So, but I think it is good for debugging, seeing if your learning rate's going down, if you're actually learning the stuff that you want to learn. So I think it is useful, but I've yet to use it. So.
No further questions? Okay, the next session will be in a month, more or less. It's about big crisis data. Carlos Castillo, he's the director of Eurecat. Eurecat is a research institute. It's near here. It's near the UPF, and he made a lot of research about, let's say, data science for the social good and these kind of things. And well, he's also writing a book. But you can check the meetup website, and there's a lot of information. Apart from that, again, I want to thank Vistaprint, and there are some snacks there if you want to talk and have something. You will be welcome. Okay. Well, and thanks, Vistaprint.